Okay, so we're starting definite integrals today. And this is Leibnitz. He's one of the creators of calculus. We'll talk about him a little bit today. So, where do we start? Well, when we find the area under the curve by adding up these rectangles, we've been doing rectangular approximation, the answer is called a Riemann sum, or Riemann sum. Okay? Now, the width of a rectangle is what we call a subinterval. The entire interval is what we call the partition. Okay? Now, subintervals do not all have to be the same size. Okay, especially sometimes when our function is not as steep, like here from 1 to 2, we can use bigger subintervals. And then from like 2 to 4, it'd be better to use smaller ones because the function is more steep and we have more missing area. So it just depends on how we're doing things. Plus, we've done tables where the intervals aren't exactly the same either. Okay, but when we add up a bunch of things in succession, we can use sigma notation. Okay, sigma is the Greek letter right here. This is sigma. That's what sigma is. Okay, and in sigma notation, it's a way of adding up a bunch of terms in sequence. Okay, so in sigma notation, k tells us where to begin the sum. Okay, so that's the number below the sigma. So in this, k is 1. And where to end at the number above the sigma. So in this case, it's n. And if the symbol infinity appears, it indicates the terms go indefinitely, or we have an infinite number of terms. But you can see here, k is 1, so we start at k is 1. And so we take a1 plus a2 plus a3, and we keep adding until we get all the way to an, and that's where we stop. Okay, so this idea of adding a bunch of things up is what we've been doing with rectangular approximation. We'll find the areas of all those rectangles and then we add them up to find the approximate area under the curve. Okay, we've kind of been doing it without really thinking about the notation itself. Okay, so going back to this idea of subintervals and partitions, if the partition is denoted by p, okay, and the length of the longest subinterval, so the biggest width rectangle, is what we call the norm of p, and it's denoted by these, they look kind of like absolute values, okay, brackets, but they're not. Okay, that means the norm of p. That's telling you how long your longest subinterval is. Okay, now, if that's the case, as the norm gets smaller, the approximation of the area gets better. Okay, and we've talked about that. So if we wanted to get a better approximation of this area under the curve, we could use smaller rectangles. And the smaller the rectangles, the smaller these subintervals get. So if we cut these again in halves or halves again and made them even smaller, we'd get a better approximation. Okay? We've seen that happen again and again. So now we're saying, okay, the area then, and this is a big ugly equation, but breaking it down, we are saying this, what is this again? This is the norm of p, so that's the width of the rectangles, okay, is going to 0, so the width is getting smaller, right? This f of c, k, that is your height, okay, and this is your width. And remember, sigma adds up a bunch of stuff. So what we're saying here is literally that we're adding up, sigma is adding up height times the width, which is area. And we're adding up all these areas, but we're doing it as the width itself is getting smaller. So small, it's practically getting close to 0. So we're bringing back that idea of a limit, okay? And in this case, our limit's going to 0 so that our widths are getting really, really, really small, which means my approximation is getting better and better and better, okay? All right, you with me there? So this is what we call the definite integral of f over the partition a to b, or the distance from a to b. Okay, Now this right here, this is kind of how Newton had set up his definite integrals, okay? But basically, if we say we use the subintervals of equal length, then the length of the subinterval is the change in x, the total change, which is this distance from A to B over n, which is our number that we're stopping, okay? Then what ends up happening is that the definite integral is then given by this equation, because the norm of p, there is no norm because they're all the same interval. And this is still going to be length times width. This is still area. We're still adding up the areas, okay? But in this case, the area or the change in x is the same. It's a constant. That's why we don't have to change it for everyone. So see, this and this were the same because this had to match. But since delta x is going to be the same no matter what part I'm at, we don't need to add that k in. So it's getting simpler now, okay? Now, Leibniz introduced a simpler notation to define the definite integral. Okay, thank God. So these two equations mean the same thing, okay? So we've talked about this before. dx is a small change in x. That's what this is. F of x is the height, and this is also the height. This part right here is telling me to add it from here to here. That's the same here, adding from A to B. So basically these are the same equations. The difference is the way the notation is set up. Okay? And thank God, because doing the sigma all the time is not that great. Okay? So this is what we call the definite integral. That's the very small change in x. Okay? Now that we know kind of the idea of what it looks like, this is what we call the integration symbol. Okay? It actually looks like a very long S, standing for summation, adding up a bunch of stuff. This is my lower limit of integration. That's where I'm starting. This is my upper limit of integration. That's where I'm finishing. That is my integrand, or my function that gives me my heights. And this is my variable of integration, or my dummy variable. That's what's telling me my width, my change in width. Okay? Now, this is really important. You need to know the parts of our definite integral. Okay? Now, here we go. So, we have the notation for the integration, but we still need to learn how to evaluate the integral. Okay? And we're going to talk more about that tomorrow. But what I do want to talk about is when we talked about this earlier example, we considered an object moving at a constant rate. And I basically gave you guys this. And we talked about how velocity, the area underneath the velocity, is distance. Okay? Now, if the velocity varies like this, okay, we've been working on how to go from velocity back to position. So in this case, this is my velocity equation. This is my position equation. This function s of t is the antiderivative of velocity. So if you work backwards, or you can see perfectly fine that if you took the derivative of s, you get v. Okay? But we've been talking about this, about how this function here, the velocity, is s prime of t. And we've also been talking about how to get from velocity back to position if we need to, and finding that constant. Okay? But let's keep going. That means that if we're looking at this velocity curve, and this is the graph right here, okay? After 4 seconds, the distance it's traveled is 8. So if I take my position equation and I plug in 4 for my time, that gives me an area or a distance of 8. But if I use this picture, if I go and find this area right here, because it's a trapezoid, and the area of a trapezoid is 1/2 height times base 1 plus base 2. Okay? And you can see right here, this is base 1, this right here is base 2, and from here to here, that is the height. Okay? And that area is also 8. Okay? So now we have two ways of finding area. We can either break it up into pieces that we know, or we can take the antiderivative, work backwards from my velocity to my position, and plug it in and also find my distance. Okay? But what happens when we have this? Okay? When we have this curve like this, and again, we've been doing it with rectangular approximation, but let's try what we've been doing recently by working backwards. So if we have velocity and we work backwards, since velocity is the derivative of position, we can find the antiderivative. So adding 1 to the power, divide by the new power. So that's what gives me t cubed, and the antiderivative of 1 is t. And again, we just talked about it, since position at 0, time at 0 is 0, we don't have a constant. So we plug in 4, and we find our distance is 6 2/3. This is the example that we started with when we started rectangular approximation, and I told you the answer was this, 6.66 repeating. Okay? And now you can see why, is because we're actually going to start using the antiderivative to find the area under a curve. Okay? So all of this that we've been working on, talking about rectangular approximation and changing from velocity to position, finding this antiderivative and that whole area in a curve, are now merging into one idea where the antiderivative is going to actually help us find the area under the curve. And it's easiest to think about it as, if the curve is velocity, the area underneath it is, of course, position.